Well, good afternoon. It's 2:37. I'm 7 minutes late getting started. I kept waiting for someone to show up, but so far nobody has. So we'll pick up and go from where we left off last time. I think I'll wait until there's actually a body in the room before I make the 2 or 3 announcements that I need to make. Nothing really crucial, but just wanted everybody to know it and hear it. But I'll wait till someone's in the room so at least that one person hears it. I'm not certain anyone listens to these things at home. I hope you do, but I can't say for certain that you do. So let me just for a moment. Get my roll book caught up. Okay, so we're ready to go now. Where we left off last time was in Chapter 2, First Order Differential Equations, 2.4 exact equations, and we talked about what they were and worked a few examples of them. Let's now do an initial value problem, so we're on page 68, the top of the page, example 3. Here it says, solve this, dy dx. Oh, let me get my pen back to black. Okay, dy dx is equal to xy squared minus cosine x sine x divided by y times 1 minus x squared, with the initial condition that y of 0 equal 2. Okay? First order ordinary differential equation. What are some things we can say about it? Are these variables separable? I think not. Okay? I don't see any way in the world you could do that. Okay? Number 2, are they linear? Nope. The y squareds and y on the denominator are almost guaranteed that's not going to be the case. So the only hope so far with what we have at hand is are they exact? Well, they sure don't look like it written in this form, so the one thing we better do is write it in differential form and bring things to one side or the other. So let's first multiply both sides of the equation by the y times 1 minus x squared. Okay? Y times, yeah, that's right, 1 minus x squared. Okay? And then we'll also write it in differential form. Okay? And then we'll flip things around and write it like this. Y times 1 minus x squared. Well, no. Let's see. I wanted to put it doesn't really matter, but I just wanted to put the dx in front. So these go out. Okay. And I don't think it really matters which way we do this, so I'll say xy squared minus cosine x sine x dx minus, actually I'm going to make it a plus here. I'm going to switch the sides around some. Y times x squared minus 1 dy is equal to 0. Okay, that's our standard form for our exact differential equation. Just writing it in this form, does that make it exact? No, it doesn't. Not by any means whatsoever. What does make it exact is doing the test to see if that does produce an exact differential equation. Okay? So what we do is take the derivative of the left-hand side, the partial of the left-hand side with respect to dy, the first term by dy. So the partial of this with respect to y is 2xy. Huh. Because the partial with respect to y of the x terms are nothing. Over here, it would be partial of this with respect to x, and that would be 2xy. And that's it. So yeah, those two are equal, so this is an exact differential. So the test passed, so let me get these off the screen just so we can proceed from here. All right, now, the next question that comes up is, which of these looks like it's easier to do first? Well, my temptation is to do the shorter one first, okay, just to see if that produces anything nice. So basically what we're saying here, this expression here, okay, is supposed to be the partial of some f with respect, so we're assuming that there's some f of xy equal to some constant c. That's what we're assuming. And we're wondering, the partial of that with respect to y should be this thing. So we're saying the partial of f with respect to y, we're hoping is going to be this thing right here. Y times x squared minus 1. Okay? Now, if that's the case, we can basically write it as a derivative. Okay? And integrate both sides. Okay? And what we would have then is f of xy is equal to, well, integrating this with respect to y would be x squared minus 1, that has no y dependence in it, over, okay, I was jumping a little ahead, x squared minus 1, y squared over 2, okay? All right, plus some g function that is a function of x alone, g of x. Okay, we haven't been doing it this way. All right, now, with that in mind, let's see what happens if we take derivative of this thing, of this f, with respect to x, the partial with respect to x. I'm running out of room, so let me do it here. Partial of f with respect to x, then, would be the y squared over 2 is just a constant, so we'll do y squared over 2 as a constant, and derivative of this thing with respect to x would be 2x. Well, the 2's cancel out, okay, and you just have xy squared, okay, plus derivative of that with respect to x would just be g prime of x. Okay, now, if you look here then, that's what this is supposed to be, partial of f with respect to x. Well, there's your xy squared right there. So this would indicate that g, I'm going to write it this, d by d, dg dx is equal to minus cosine x sine x. Okay? All right, and let's just do a dx on both sides and integrate this, and you get g is equal to, and what's the antiderivative of minus cosine x sine x? Well, pretty sure that would be cosine squared x over 2. Okay? We probably will need a plus c, but let's just check this one first. Derivative of cosine squared x dx would be 2 times cosine x times derivative of cosine x, which would be minus sine x. So yeah, that works, and the 2's cancel out. Yeah, that's it. Now, is this the place that we put? No, I don't think we need a plus c here either. So there's our g of x. So let's write out our answer. Okay, this f of xy is equal to, where did we write? There it is, okay, is equal to x squared y times, I'm trying to write it the same way I had it before. Okay. All right, down here. X squared minus 1 times y squared over 2 minus, no, plus, your g of x was cosine squared x over 2. Okay? And that this is equal to some constant c. Well, let's just multiply everything by 2 and make it some other constant c. Okay? So here's what I'm hoping our answer is. Is equal to a constant c. We have an initial condition. Y of 0 is equal to 2. So when x equal 2, y is equal to 0. Okay? So let's plug that in here. And x equals 0, 0 squared would be 0, minus 1 times 4, so that's minus 4, plus cosine squared of 0, well, cosine of 0 is 1, so cosine squared plus 1 is equal to c, so this would be c is equal to negative 3. If I did that right, okay? So now let's go back and plug all this back in, and it's x squared minus 1 times y squared, yuck, plus cosine squared x is equal to minus 3. Yuck. Now, just looking at that, that's not very satisfying. Well, yeah, it can be. Okay. Because this would require the 1 to always be greater than or equal. The x squared was always less than or equal to 1. Okay? So x has to be between minus 1 and 1, I think. Let me see if I haven't made a dumb mistake here somewhere. And we got y squared times x minus 1 squared minus cosine squared x is equal to 3. Okay, they just multiplied everything by minus 1. Now, and I mean, that's the same answer we have, only multiply the first term by minus 1 to reverse those, then a plus sign there and a plus sign there. So yeah, that all works. And they show a lot of the level curves here, solution curves, for example 3, and then in blue they put the one that makes this work. Now, and again I said x has to be between minus 1 and 1. And you see, indeed it does in that picture, figure 22.4.1. And the reason for that I said it, is this thing has to be negative. Because that's positive, this thing has to be negative in order for that to add to be a minus 3. So the x squared minus 1 has to be, so x has to be between minus 1 and 1. It can't be greater than, it can't even be equal to 1 or minus 1. It has to be less than. And then the y-squareds can be quite big. As long as that first term is negative, the y's can be quite big, and then the cosine, of course, that's sort of fixed. That's between plus and minus 1. But cosine squared is not between plus and minus 1. It's between 0 and 1. So that does appear that would be a reasonable expectation there. Okay. Okay. Now, and one thing they suggest is that then we do solve this explicitly for y squared, not explicitly for y, but explicitly for y squared. And that would then for the life of me, I can't see right now any reason why y can't be negative. Oh, because of the initial condition, of course. Okay. All right. So that isn't quite the end of it. Okay. This is how you do differential exact equations, even when they look really, really, really bizarre. That as long as that initial condition is met, I mean not initial condition, the test values are met. Okay? Now, they point you back to 2.3 that the left-hand side of a linear equation can be transformed into a derivative when we multiply by an integrating factor. It says here the same basic ideas sometimes work for non-exact differential equations that look like they could be exact, but when you do the test, they don't. That is sometimes possible to find an integrating factor, mu of xy, so that after multiplying the left-hand side of the equation, which, I mean, multiply both sides, but the right-hand side is 0. You're my only student so far. Thank you so much for being here. Daniel is here. Dan is here. Okay. Let me swap out my lights. I'm not projector. I'm talking to myself. I don't need the projector at all. Okay. I promised before, while this is coming on, I was going to fulfill the promise to make the announcements after somebody got here, so at least one person would hear it. I can't guarantee that if I say them to the screen that anyone will ever hear it, but so this way at least one person will. This is, and I'm kind of preaching to the choir right now because, well, it may not be, but anyway, this is rapidly approaching what we call midterm. Okay, because midterm is midnight Tuesday night. Okay, and midterm Tuesday, that means that sometime after midterm, they usually request for us to give them a midterm progress report, which is people who have D's or F at midterm. Now, right now, one person in the class has turned in a document that can be counted as a grade. Okay, so that means the other 5 of you I have nothing for. Okay, so I need something, preferably this week. Okay, so if you can get me something, either the research paper or that first test, either one. Okay, that would be fantastic. Not that it means much because it has nothing to do with your final grade or anything else. It just means you might get bugged by somebody saying, oh, do you need tutoring, or do you need counseling? Do you need something, in order to get your grades up? So to avoid that potential hassle, whether it would happen or not, I don't know. It'd be nice to have some score before the end of the week, if possible. Okay. Now, sort of, just mildly dovetailed with that is the fact that on Friday, I'm not going to be on either campus. Okay. I have a meeting down in Montgomery. It's called an articulation meeting We tried to speak clearly. No. It's the 2-year colleges, 4-year colleges get together every year and go over any issues with transfer courses and things like that. And so that meeting, I've been assigned to this committee or this group, whoever it is, and we have a meeting. South Alabama hosts it, so it's in Mobile. So that means Friday morning I leave the house right as soon after 7 as possible, so I can drive all the way to Mobile and be there hopefully before noon, okay? Because the meeting starts at noon. And for a big 3 hours, I have just driven 4 to 5 hours down there. We'll meet for 3 hours, and then I'll turn around and drive 4 to 5 hours back. So for 8 to 10 hours of driving, I attend the 3-hour meeting. And I thought somehow I could talk my way out of it, but they said, no, I need to go. So I'm going to be going. The previous meetings, they've all held during the week or sometime when I couldn't go. This one, they're holding on a Friday, so I don't have any excuse other than it's so inconvenient, terribly inconvenient. Why wouldn't they have it at least Montgomery or somewhere like that? Nope, Mobile. So anyway, I'll be off campus. I'll be out of the city and, you know, in the state, out of reach all day Friday. Long day. Get home probably about 8 o'clock at night. So 11-hour day. No, 13-hour day. Depending on how traffic goes and stuff like that. Maybe home a little sooner. Okay, so that's Friday. The following Friday, not that it really matters that much, because I know you're never coming on Friday, but I do have a doctor's appointment, eye appointment, just across the street here at UAB West. I thought it was going to be at Eye Foundation Hospital, and he said, no, that Friday he happened to be at UAB West. I said, well, I'll work right across the street from there, so not bad. But I'm supposed to be on Birmingham campus, so what I'll do, I'll drive here, go to my appointment. It's 8:15, so it's early. It's as early as I can get it, I think. And I'll be there at 8:15, and hopefully it won't take more than 9:15, more than an hour, or whatever. Whenever I get through, then I'll come back and probably drive on to the Birmingham campus, because I have at least one student who likes to meet with me there. She's doing an independent study, and I guess I need to do that, especially since I'm not going to be here this Friday. I'll need to be here next Friday for her. And it's but the only thing is how messed up my eyes feel after they've done whatever they've done to it. Usually it's no problem, and I can wear those dark shades and drive okay. But if I'm having problems, I don't feel like I could drive safely. I may work for a few hours here, but what could I be doing if my eyes are out of commission? But yeah, hopefully I can do something. And then when they feel better, go over there. But I'm hoping to be able to just go over there. So that will be Friday, the following Friday. I'll be late getting to Birmingham, but I'll be there. I'll be here earlier, but over there most of the time. Then drive to Birmingham. All right. Then shortly after that is spring break. So anyway, let's move on. I just finished, as you see here, example 3, and did some blah, blah, blah talking about it. I was just beginning to talk about integrating factors, which is on page 68 at the very bottom of the page. And here's what the deal is with what they're talking about there. We had integrating factors before to make a linear differential equation workable. Here we're going to be doing one for this. So here's what they mean. What if we have a differential equation, m of xy dx plus n of xy dy equals 0. But what if this m and n don't pass the test? In other words, there's no way you can do the partial of m with respect to y. You get something, you do the partial of n with respect to x, but you get something else. So they don't pass the test for this to be an exact. So this would be an inexact differential equation. Okay? well, they say, what if there was some integrating factor, mu of xy, that you could multiply by, and then you would have mu of xy times m xy dx plus mu of xy in n of xy dy equals 0. And what if this magical mu you came up with made it so those two factors, that the partials, your test partials that you did, made it so they were equal? Then you could do this, okay? Make it an exact differential, okay? In an attempt to find that mu, we turn back to, and it says criterion 4 for exactness. And I don't even remember where criterion 4 for exactness is. Here we go. Theorem, yeah, page 65, bottom of the page. Oh, that's what they mean. It's the same thing I've been talking about. Okay, sorry. So that same thing. We turn to that for exactness. Okay. Equation 8 is exact if and only if the partial, with respect, I'm going to leave off the xy's now, mu m with respect to y is equal to the partial of mu n with respect to x. Remember, that's what our test was, the criteria for this to work. Okay? Now, if that's the case, and I wrote them this way, they wrote subscripts for partial derivatives, by the product rule of differentiation, the last equation is the same as okay, let's do this equation. This with respect to y. This is the partial of mu with respect, wait. Before I do this, I want you to do it. Take the partial of mu m, product rule. What would that be?
We're at the bottom of 68.
Second?
We're at the bottom of page 68.
Yeah, down there.
Okay, so we're taking the
Okay, the product rule says,
so we have the mu.
okay, the first mu times the
Derivative of
m with respect to y plus
the derivative of mu
partial of mu with respect to y times m, right?
Yes.
Okay, that's equal to, do the same thing here, mu
with respect to y.
Okay, you're going to do the partial first. Okay, partial mu with respect to x, I think it is. They've already changed sides. Okay, I'm trying to do it just straightforwardly. Okay. Okay. I'm trying to, they're skipping some steps. I'm showing you where the steps come from. Product rule here says first times the root of the second plus the second times the derivative of the first equals, and then I thought you were going to do the other.
Yeah, I probably should have.
Yeah, okay. Well, they skipped steps is what it was. So you like to do first, mu partial with respect to n with respect to, partial of n with respect to x plus, I like to do the n now, partial of mu with respect to x. Okay, those two are equal. Now, what we're going to try to do is get the mu's all together. Okay? They did them in reverse order from what I'm about to do, but let's get the mu's together. here are the two mu's, so you subtract this here and move that one over there. So that would give you, hopefully I'm not skipping too many steps here, the mu here, this would be partial of m with respect to y minus partial of n with respect to x. Also, those are the two terms with mu's in them. Subtracted that from this side. That's equal to and it really doesn't matter too much, so I'll do it the same way they did. N times the partial of mu with respect to x minus m times the partial of mu with respect to y. That's subtracting this from both sides. I rearranged a little bit. Okay. Now, to just a little time out here. Okay. Remember when we first did this, before we did the partial here, first thing we did was check to see if partial of n with respect to y was equal to partial of n with respect to x, right? And we saw it didn't. It wasn't. So therefore, this term here we know is not 0, because this is partial of n with respect to y minus partial of n with respect to x. If they were the same, this would be 0, and we wouldn't even be doing this. So now we know this isn't the same. Here we've already done these partials, so this is nothing new. We did it, didn't work, but hang on to them, and then we put them in down here. So we know what they are. You know, we already calculated. Okay? So this is just some expression in x and y, perhaps. Okay? And that over there, we assume is some expression in x and y as well. Now here's where the magic comes to play. Okay? The thing. Although this m, this n, this m sub y and this n sub x are known functions of x and y, the difficulty here in determining the unknown, mu of xy, from this equation that we have right here, is that we must solve a partial differential equation. Since we're not prepared to do that, are we? Okay. We make a simplifying assumption. Suppose mu is a function of one variable, for example, it depends only on x, or only on y, one or the other, but not necessarily on both. So why did we start off saying mu of xy? Why didn't we make this assumption to begin with, saying, otherwise we can't do this, okay? But we carried it this far, and now we're going to back off and say that's what we're going to do, okay? Suppose you as a one, say mu depends on x. In this case, then you don't have a partial of mu with respect to x. You just have d mu dx, okay? All right. And the other one, d mu dy, this one is 0 because mu depends only on x. That's the assumption we're going to make now, that mu is strictly a function of x alone, not y. So we can talk about the derivative of mu with respect to x, but the derivative of mu with respect to y is 0 because it doesn't depend on y, okay? Or those partials don't, okay? So that's our simplifying assumption here, okay? With that in place, then here's what we've got. Oh, I was on the wrong line. I said, how did they do that? No. If we're assuming that this one is 0. Yeah, this drives me nuts. Okay, so what we've got now is that mu of x and x alone, no y dependence, from right here, there it is, okay, is equal to, this is 0, so this is n times the derivative of mu with respect to x, it's just a function of x alone, divided by this thing here, and I'm going to shorten this, m sub y minus n sub x. Remember, we already did that. We already figured out what m sub y and n sub x was when we first started. So we didn't throw that away. We used it here. And that difference, not 0, is going to be there. So now we have mu, a function of x, is equal to this. Okay. Now, the problem here is that this, n, depends on x and y, and these partials could depend on x and y as well. But this side only depends on x. We've already made that assumption here. So we're hoping, beyond all hope, that all the y's are going to cancel out on the right-hand side, so we do have an equation that's only in terms of x. Okay? That's what we get down to here. Okay? If that's the case, then this is a first-order ordinary differential equation. We can either determine mu because it's separable as well as linear, blah, blah, blah. So we go on from there. Now, all this is only going to give us our mu. It's not going to solve our problem. It's just going to give us our mu. So here's our mu is the n. Okay. All right. Here's the problem, though, the way I've written it and the way they've written it. Okay. They're solving for this, so this merely says, and here I've got to do some erasing here, so I'm going to start here, and I'm going to erase this line right here. We've already dealt with it. We've done it. So rather than solve, I was just showing you here what mu sub x is going to be, but we don't know what it is. So here we get our differential equation. D mu dx is equal to, multiply this, so this would be mu of x only times m sub y minus n sub x divided by n. Okay, and that's what they have. And here is where they're saying, hopefully, this thing here, all your y dependence is going to cancel out. If it doesn't, this isn't going to work. But if it doesn't, then turn around and do the same thing, only make your mu as a function of y, and then rearrange things. Okay? And we'll get to that in just a moment. Okay? Now, and what they're saying here, this is a separable differential equation. You can divide both sides by mu. Okay, okay. Yeah. This will be, you can write this as d mu over mu if you divide by this. But remember, this we're assuming all the y's are going to divide out, and then this will be only a function of x dx. Separate the thing, integrate both sides. This will be a log y, a log mu. Okay, let me write that stay in there. Okay, so what happens here, this is assuming in this side here, and this thing right here, all the y's have divided out, disappeared somehow, magically. Okay, and then you have here derivative of mu over mu when you divide this, right? And then it's equal to this thing here, m sub y minus n sub x over n dx. Now we've already assumed that all the y's are going to disappear in that. So here, you just integrate these things. Okay? And this gives you log mu is equal to this integral. Okay? Well, if I want to know what mu is, then I'll raise it to e to the integral of my minus nx over n dx. Okay? All right. So this is all a function of x integrated. Hopefully you can do the integration. Whatever that turns out to be, e raised to that, that's your integrating factor. Okay? Now, that hasn't solved the problem for you. Let's just set it up so you can solve the problem. Okay? So your integrating factor, mu, is some function of x alone. And now, I think I have to erase all that also in order for it to make some sense here. I'll erase the stuff below it, okay, because we'll hang on to that. Oh my goodness, well, wonders never cease. Okay. Muhammad is here. Before I said, okay, and for next time, oh no, okay. All right. Yeah. Okay. We're now on page 69. We don't have a book anyway. We're doing exact equations. I'd already done example 3. That worked out pretty nicely. Now we're saying, what happens if our test fails? Remember, when doing exact equations, the first thing you do is you do the partial of this with respect to y, partial of this with respect to x. If they're equal, you can do an exact equation. Okay? If they're equal, you can do it. Now we're saying, what if they're not equal? Okay? Well, then let's see if we can come up with a multiplying and integrating factor, mu, to make them equal. Okay? And we started off saying that mu was a function of x and y alone, and soon we found out we can't do it if it is, because then your partials are all mixed up. So then we backed off and said, well, let's let mu be either a function of x alone or y alone. Okay? And if you did, and I'm already started erasing this, so I can't reproduce it all. You'll have to watch it to get it. But here's what we're doing. I think that, yeah, this is still my eraser here. We came up with what that integrating factor was if mu was a function of x alone. And here's the integrating factor. I'm going to take this out too. I don't think I need it any longer, because I'm going to need a bunch of white space. Okay. So here's our integrating factor. A couple things had to happen. The mu is a function of x alone, and even though n was a function of x and y, and therefore probably partial of n with respect to y and the partial of n with respect to x were factors of x and y, we're hoping beyond all hope that this thing right here, all the y's divide out, and you wind up with a function of x alone, so this can be a function of x alone. If that happened, proceed. If it didn't happen, try something else. Okay? So we're assuming it did. There's our integrating factor. So what do we do with it? We go back to our very first here, and now the mu is a function of x alone, or that's our assumption now. So I'm going to take out the y's here, okay, and take out the y up here too, okay, a function of x alone, okay. Yeah, and that's the integrating factor, okay. So now we do mu of x, m, still a function of x and y, times dx plus mu of x times n of x and y dy is equal to 0. Now, everything we've done Okay. That should now be something that we can do. Go back and check and see if they are indeed, if the partial of this with respect to y, which this won't contribute anything to, is equal to the partial of this with respect to x, which will have this and that in it, x dependency in it, and hopefully those will be equal now. Everything we've done would indicate they have to be, but they would be, and then you go on and solve it. I think when we actually do an example, it'll make more sense. Too many hypotheticals right now. If, however, you could not get this condition to be met, that mu would be a function of x alone. In other words, this, when you did this calculation here, it did not, the y's didn't cancel out, then stop, because everything depends on that. But then you reverse it and say, well, what if mu was a function of y alone? And if it was, this would be the case then, that the mu, now a function of y alone, would be similar to this, e to the integral of, I'm pretty sure it's n sub x minus m sub y over m dy. And that's a function of y alone. So if it didn't work out that this was a function of x alone, then try this and see if that would be a function of y alone. And if it is, then you use that as your mu and proceed. And then it would be a y here and a y there. Okay. So that's what we're hoping is going to happen. Okay? And let's make sure I got it right.
Is there a case where you can use either or?
What's that?
Is there a case you can use either or?
Yeah, it could be either or. Well, wait. It could be that it could be either way. One might be easier than the other, or it may be that it's only one or the other. But it could be that it's neither. And if that's the case, you can't do this. You can't do it by exact. We're hoping it can, and we're hoping the ones they give us will be. Okay? So what it breaks down to is, in my mind, okay, it's these two things. This thing right here, if that's a function of x alone, we're great. Or if it's not, if this thing right here is a function of y alone, we're great. If it's not, neither one of these will work. But if
I think you circled the wrong. You should have circled the one underneath that.
well, yeah, that's the same thing.
Yeah.
The ratios are the same.
All right.
Yeah, yeah. So, and the thing is, we've already done it. We already took the partial of m with respect to y and the partial of n with respect to x. So really, this seems like a lot of work. But really all it is things we've already done. Okay? So let's see the example. I hope it'll make it make more sense. Okay? It seems like they throw all this stuff in there and leave out the simple. Okay. So let's see. Maybe, maybe not. Let's see. Here's a nonlinear first-order differential equation. xy, I can't write, dx plus 2x squared plus 3y squared minus 20 dy is equal to 0. Okay? Now, that's written as if it's in exact form, the differential form with a 0 on the other side. That looks like an exact form. What's our test?
Partial with respect to x and partial.
Okay, partial of xy with respect to y, the other one, right? And we'll do the partial of 2x squared plus 3y squared, I hope I wrote it right, yeah, minus 20 with respect to x. Okay, what's the partial of this one with respect? Yeah, this will just be x. Okay, and what's the partial of this with respect to x? Say again? This is 2x squared.
Yeah.
Partial of 2x squared is 4x, right?
Plus.
No, it's 4x, isn't it? 4x. And then the others don't have an x in it. No, they're not equal. They're not at all equal. Okay? They're close, but not equal. Okay? So, but here's our partial of the m with respect to y, partial of n with respect to x. Well, what we want to have is either a mu sub x such that, and okay.
How about if we try with respect to y?
What's that?
We try with respect to x.
Well, we did this one with respect to y, this one with respect to x. So we've done our tests, and they're not equal. So now we're going to look for an integrating factor that might make them equal. Okay? Now,
How we got with respect to y? How we got just x?
okay, say this one more time.
With respect to y, we have just x.
Oh, dy equals dy.
It's the partial of this thing here with respect to the other one, y. Okay. The partial of xy. This is our m of xy. The partial of m with respect to y. Okay? And that is just, this is treated as a constant. Partial of y is 1, so it'll just be the constant times 1, x. And over here, partial of that thing, the n of xy, with respect to x, because that you do it with the other one, is just 4x. Okay. Now, it smacks to me now as if maybe our integrating factor should be with respect to x, because these both have x's in them. But maybe my thinking is wrong. Excuse me, I've got hiccups terribly. Okay? Now, if you did I wish I hadn't erased all of it, the m sub y minus n sub x over n, there's no way that's going to produce. So, no, going mu sub x, that's not going to work. The mu sub x was, I don't know if there's an easy way to remember this, but if you look up above, the mu sub x is dominated by the n's. It's m sub y minus n sub x, which this is the m sub y right here. So that would be x minus 4x. Like I said, these things we've already calculated. But then you divide that by your n. Oh, no, not that. 2x squared plus 3y squared minus 20. There's no way you're going to eliminate and make that a function of x alone. Not going to happen. But the other one, the mu sub y, this sounds like, I mean, mu is a function of y, sorry. This would be your n sub x minus m sub y over m. Okay, m, here's the key. That's the simple one. That's the one we want to use. Not the fact that these are still going to be pretty simple. This is 4x minus x is 3x here divided by xy here. Ha! Look at that. The x's go out. This is a function of y alone. That's what we want to happen. The other one, no way that's going to be a function of x alone. You got those y's in the denominator you can't get rid of. But this one, yes, yes, yes. In other words, this is a pretty simple one here. If that's what you want to divide by, that's the one that gives you your thing there. Okay? And that gives you a function of y alone. Okay, well, what do we do with that? We integrate that. The integral of 3 over y dy, and that's going to be 3 times the natural log of y, right? Yay or nay? Yeah. And you don't ever put a constant on this, okay? And then you're going to raise that to the e. Well, before I raise it to the e, let's make that log of y cubed. Remember, that's one of the properties of logarithms. And I've got my thing all wrapped up. And I know what that is. This is just y cubed. There's my integrating factor. E to the integral of that thing. That's the integrating factor. That's my mu of y. So I'm going to go back to this first equation here. And rather than having that, I'm going to multiply by that. So this will give me x y to the fourth, because I'm multiplying by y cubed, dx plus, I'm going to multiply each of these by y cubed, 2x squared y cubed plus 3y to the fifth minus 20 y cubed, I'm sorry, I almost forgot that one, dy. What's that?
I thought y was the square. Oh, you added it to
Yeah. Legal?
Yes.
Okay, good. Okay. Multiply everything. Okay. No. What's that?
You combine it 2 steps.
Yeah, I'm sorry.
Yes.
Yeah. Okay. Yeah. Multiplying each of these terms by y cubed and that one by y cubed. Now let's check and see if our conditions met. The partial of this with respect to y would be 4xy cubed. Okay? Partial of this with respect to y would be 6x. Ooh, this is a look. No, sorry. This with respect to x. The second one with respect to x. This with respect to x would be 4xy cubed. This has no x in it. That has no x in it. Look at that. They are equal. So therefore we can use our exact differential on this one. Trouble is, it's not the same equation we had before, okay? It's just multiplied through by some other. So we've got to get there at the end. Okay, did you have a question?
No.
It sounded very certain. Okay. This is now our differential equation. Yeah.
I'm with you up to the point that I was under the assumption that when we were trying to find if they were equal, we were looking for respect to x and respect to y, and that's effectively what we've done here at that last one. So
Yeah. Okay. We did the partial of this with respect to y and got this one,
right,
and the partial of this one with respect to x, and that only gave us this one, and those are the same. So now we can proceed with our exact differentials. Okay. All this is just to set it up so we can do it. This hasn't given us an answer, it just gives us the capability of getting an answer. So this is our differential equation. So we don't need this anymore. We don't need that anymore. We got that they were equal. We don't need any of these anymore. y'all can have it all written on your piece of paper. I just don't have enough paper up here to cover it. Okay. So, let's see if we can solve this differential equation. Okay. Now remember the assumption here in an exact differential is that we have some function f of xy equal to some constant c. Okay. That's the assumption, because when you take the derivative of this, you'll get a 0 there, and you take the partials of this with respect to here. So this is saying, if that is that, this expression right here is going to be the partial of f with respect to x, right? Okay, because if you were to take the derivative of this, you say partial of f with respect to x dx plus partial of f with respect to y dy is equal to 0. And that's what we would have. So this thing right here should be the partial of f with respect to x is equal to x y to the fourth. Okay? So let's multiply both sides by dx, which is not quite legal, but we're going to do it. Change the d to the delta. I mean, it's all sorts of math rules we're breaking here. Integrate both sides with respect to x. Okay? Well, this is with respect to both, and this gives us f of x and y. Okay? The integral of a perfect derivative is just what's left. So we integrate this with respect to x. Well, the y fourth is like a constant, so let's pretend we move that out front. And the antiderivative of x would be x squared over 2. So this will be x squared y fourth over 2. Okay? Plus, there still may be, we integrated this with respect to x, could be a constant left over, but remember our constant could be a function of y, because we didn't integrate with respect to y, only of x. So there would be what that would be. Well, again, we don't add any plus c's or anything at the end. We'll get to that later. Well, remember, this thing right here is going to be the partial of f with respect to y. That's how we do our partial. If we're taking a partial derivative of this, the partial of f with respect to x dx plus the partial of f with respect to y dy is equal to the partial of that is 0. That's what our assumption is, that we have some f that works on. So this expression here needs to be this, partial of f with respect to y. So let's take the partial of this f with respect to y, which means we'll take the partial of this with respect to y, and take the derivative of this with respect to y.
Right, hold up. You lost it there.
When we did this, we said this is what the f is going to be.
Yes.
This thing plus some unknown g of y.
G of y.
That's what your f is.
And
Well, we know that the partial of f is supposed to be that.
yes.
So we're going to take the partial of this thing and set it equal to that.
Yeah, I thought we were taking the partial of what you have in the box right there.
Yeah. No. This is what the partial of f is supposed to be. This is what, see, before I wrote this in, it was alpha of xy is equal to this thing plus some unknown g of y. Well, if that's what f is, then let's take the partial with respect to y of this and that and say that's equal to that. Because that is supposed to be what partial with respect to y is.
Oh, okay, yeah,
Yeah.
because it equals 0.
Yeah, well, because the sum of those equals 0.
Yeah.
Okay, so we're doing that. All right. Now, what does this say? Partial, this is just that. Okay. This is the partial of this thing with respect to y. Well, the x's don't count and the 1/2 doesn't count. That will be 4 x squared y cubed over 2, but the 4 will go into 2 will go into 4 twice. So this is going to be, doing it sort of fast here, 2 x squared y cubed. Right? Okay. Plus dg dy. Okay? Okay? And this is supposed to be this thing here. 2x squared y cubed, hey, that's looking good, plus 3y to the fifth minus 20y cubed. Okay? This partial with respect to f is supposed to be this, because that's supposed to be partial with respect to f. Okay? Now, these two terms are identical. So, subtract.
Where did you come up with the fact that they are identical?
Well,
I
this
got
is the partial of f with respect to y.
Yeah.
If this was f of xy was this plus that, and take the partial of that with respect to, and that would be what this is. We just don't know what the g is. Okay? And when you take the partial of this, you get this plus whatever that derivative of g, which we don't know what it is. And from this, we know those. But these two are exactly the same, so you can subtract them off. And now we're just looking for see what g is.
I'm still a little lost.
Okay.
I got that these two are the same.
Right.
3y to the fifth.
Okay, where did that came from? Right here minus this right here. See.
Okay, so we haven't taken this and added it to anything. We just
Okay.
compared the two.
Yeah, we said if this was our f, then take the partial with respect to y of that f, and this is what we got. Okay, we just don't know what this is. That's what we're looking for. But this partial with respect to f has to be this thing because of this.
Okay. Now you've canceled these out, so now we got dg, dy.
And look at that. That's a function of y alone. Yes, it needs to be. All right.
I just didn't let you finish. My bad.
Okay. Now, what we'll do here is write this, dy, multiply both sides, however you want to say it, integrate both sides. These are all gone. Okay. And what do we have? G of y is the antiderivative of that. And what's the antiderivative of 3y to the fifth?
3y 6. No,
Yep. Over
3y
6.
to the 6.
Over 6, right? Remember, you always divide by the n plus 1? It's the reverse of taking a derivative.
Oh,
So this is,
okay, yeah.
Yeah.
So, yeah, it's going to be.
so 3 over 6 will be 1 over 2. Okay? That's the first part. Minus
Y 4 over
4, but 4 will go into 25. So we don't even need anything over. All right. And here, too, we don't need a plus c. So we go back to our form here, and I'm rapidly running out of room again. And let me get rid of a little bit here. This I just wrote up here so we could know what we were talking about. So let's write our answer here. Remember, we said the f of xy is equal to, and before I wrote this in and this in and this in, it was x squared y to the fourth over 2, this right here, plus g of y, but here's our g of y, plus y to the 6th over 2 minus 5y to the 4th. That's your f of xy from here. It's just that we now found what the g of y is, put that in its place, and then once we have that, we set it equal to some constant c. That's our one parameter solution to this equation. Okay.
No, I hate to interrupt, but it is time.
Is it? How did that happen? Okay. Let's just see what the answer is. 1/2 x squared y to the 4th plus 1/2 y to the 6th minus 5y to the 4th is equal to c. Now, and that finishes the section too. The part that leaves me a little less than satisfied here, I'm sure there's nothing that leaves you less than satisfied, is the fact this wasn't the same equation we started with. We multiplied something by it. But we multiplied the same thing on both sides, so I guess the solutions would be the same. I haven't seen anything that proves that, but there's nothing that would indicate it wouldn't be. That's the only part they sort of glossed over really big time here. We were doing a different differential equation we started with, but it's just one function multiplied. Homework exercises, as long as they're in the back of the book, any of the odds 1 through 19. Any of the odds in the back of the book from 21 to 25. Any of the odds that are in the back of the book, 27 if it's in there, 29 if it's in there. Any of the odds 31 to 35 if they're back there, 37 if it's back there. And 39 if it's back there. I'm not absolutely certain it is, but if it is, go for it. The discussion problems are almost never back there. The mathematical model is usually not back there, so I wouldn't worry about those too much. The computer lab assignment, we don't have a computer or a lab, so we won't do that either. We'll start next time by 2.5 solutions by substitutions, which sounds like a whole bunch of fun. And by the way, just to give you a reference, this is a very short section, and then there's the numerical method we'll do, which is not super long, and that's it for Chapter 2, so we'll be having our Chapter 2 test pretty soon. Now again, I said this before you came in, but I waited till Dan got here. Midterm is Tuesday at midnight, I believe. Okay, that's right smack in the middle of the term. Before that, we're in first mini-term, after that, we're second mini-term. So sometime after midterm, they usually ask for midterm progress report, which means we have to tell them who has D's or F's at midterm. They don't care about A, B's, and C's. So I need sometime, hopefully by the end of the week, something, either a research paper or the first test. Okay? Well, sometime pretty soon I'll be giving you the second test as well, but that's a different issue. Now, midterm progress reports really don't mean anything, except it may mean you'll start getting bugged by somebody. It may not. That someone say, do you need tutoring? Do you need some counseling? You know, what's the problem? You know, you may get being bugged by people, which is good. It's a good thing, especially for younger kids, you know, but y'all don't need it, I don't think. So y'all are working pretty hard. So I hope anyway. But yes, okay, good. So please try to get me something. They may not come up with it. We're in the middle of SAC stuff, and some things may get slid this time. But then too, they may come up with it as well. Now, on top of that, I'm not going to be on campus, either campus, on Friday. I've got to go down to Mobile for a meeting, and I'll be leaving home by 7 o'clock, driving 4 to 5 hours to get to Mobile, hopefully before noon, and 3-hour meeting, and then driving back, hopefully by 8 o'clock that night. So I won't be on either campus at all on Friday. The following Friday, I have an eye appointment right across the street here, so I'll be in here early, like 8 or so. I'll go across, have my eye appointment, and then as soon as I'm able to see well enough, I'll drive on back to Birmingham. I just don't know what time that'll be. Hope to be there by 10 o'clock anyway, but I can't swear I will be. But that's a week from Friday. Next Friday, nothing. So try to get me something in Wednesday or Thursday. Yeah. Research paper and or your first test. All right. Any questions? I'll go on and shut this down. Sorry, we went a little